Okay, so we looked at these cases, right? So I'm gonna use this here. So when we have a single slit, we see this pattern, right? Just one over there. When we have a double slit, we see multiple of these bright fringes, right? And then we also saw they are at equal, they have a same spacing, right? So they are of equal width. The fringes itself have an equal width. Now, what do you think would happen if we increase the number of slits? Let's say from single to double, it looked like that. From 2 slits to, let's make 3 slits. What do you think happened? Let's make 4 slits. What do you think happened to the pattern? Do you think they will remain same, or do you think it will change then in comparison to this? So it turns out if we change so single to double, it turns out the image is going to be more like this here. Okay, so the first one, right? So first one we have here, this is from single slit. This one here is from double slit, 2 slits. So that's the Young's double slit interference we were talking about. If we increase the number of slits and make it 3 slits, then look at this. Now, here we had these, fringes, they have the equal spacing, right? Here it's no longer equal spacing, right? So see here, we see this is really bright, and then we have a little, there is a dark fringe in between, very darker part, and then we also have a bright, and then we have a dark, and then bright. But then see, this is a tiny, there is only tiny fringe here, that's red here, okay? So it's different. Now if we have a 4 slits, it's going to look like that. So you see, in the 4 slits we have actually 2 more fringes in between these large 2 bright fringes here, okay? And then if we make it a 5 slits, they kind of look almost like, like this here. Okay, so and then also note this, how the shape is changing. Yeah, this is more elliptical, kind of looked rectangular, and if we keep increasing, by the time we have a 7 slit, they look more like a circular now here. Okay, so you see, so look at this, how far they are apart. That's also important, right? These were kind of so really close, these bright fringes, but then as we increase the number of slits, the distance spacing between these bright fringes are also increasing. Okay, so as we increase the number of the slits, we can also get the interference, right? These are both again constructive and destructive interference, right? But then we call this phenomena, or we call this device, where we have this device with the multiple slits, and then when we see the pattern in the screen after using the light source behind this slit, multiple device with multiple slits, we call it diffraction. Okay, so we call it diffraction, transmission diffraction. So this is basically when we have a multiple number of slits, and which are also, this is also important, they should also be parallel to each other. Okay, so if so let us say we got like, if we make like a 1, 2, 3, 4, I mean tiny, really tiny slit. Okay, so maybe like, so how do I show this to you guys? It's you guys should have got a kit from the university this semester. In your lab kit, look at it, there is something called Gratings. Okay, so you will be able to see it has a multiple slit. Okay, So you see it looks like this kind of slide is gonna be like this, okay, so like this, but then you will see it will have a really tiny one slit here, another tiny slit that's going to look like this, another tiny slit that's going to look like this, and then multiple of those, okay. If we have this device with multiple of these slits, and the pattern we receive from this is going to be called, you know, this pattern we receive, or the pattern that goes through the phenomena called transmission diffraction, okay. And this device is a device with multiple slits is called diffraction grating. So what happens is, right, so we saw that pattern. So basically what happened is, when we put the source behind here, each of these slits are now going to act like a source of the light itself, and then they form the pattern we just saw it, okay? Like this pattern we just saw it, right? Like, so this was with the 7 slits. If we had like 5 slits, which is something like that, alright? So there is also called something called reflection diffraction grating, okay. So the one we just mentioned was transmission diffraction grating. This one is there is another type of grating that's called reflection diffraction grating, and then this one works under the principle. So these one are like, so the example of reflection diffraction grating is like this here. I have this, you know, these DVDs here. You guys can see this, right? All sign here, see color, right? Different. So what happens is, oops. So look at this. So how can we make you know, form reflection diffraction grating is really by, if we have a mirror, and then you know, we can cut it, you know, make a groove on the mirror plane of the mirror, and then when we shine a light, this white light here, what happens is the light has a different wavelength, right? It is composed of different wavelength. So different wavelength, they, you know, reflect at a different, they reflect differently, okay. So though we can make so those kind of gratings here, for example, like in this case, right, there is just a thin, so here basically we just see a different color here, because when the light, right, white light, it goes there, and then each light is composed of various wavelength. Each of the wavelength, they you know, spread in different way, okay. So that's why we see this beautiful, you know, color here, okay, all rainbow color here, okay. So this kind of you know, diffraction grating, where you know, slits are not necessarily parallel, they are called reflection diffraction grating. So next topic is about thin film interface. Alright here guys, so I'm gonna do a little bit of demo here for you guys. This is just a picture, let's do the actual demo. Okay guys, hopefully this will turn out fine. Okay, so let us see. Uh-oh, yeah, oh my goodness, it broke. Alright, so look at this so bubble. I cannot speak. Alright guys, now I'm going to explain the physics behind it, okay? I wanted to save it, but I could not. But maybe I would say at least a few things here before I go. So anyway, we have a so this, alright, I give up. So here again, I wanted to show you guys a nice bubble in the color, so anyway, so I have a picture here at least. So the interference of the light, okay, so the reason we see a color, important is color here, okay, the interference of light in the case like a soap bubble we see are called thin film interference. So that interference actually happens not just in one boundary but in two boundaries, okay? So think about this. If the light is going, what happens? Light from this, even from outside, right? Light goes, but then when the light goes, it touches the outside surface and it travels that thin film, right, soap surface, okay? Okay, and then when it goes, so it has to go in, right? And then when it goes, some of the light also reflect back, okay? So now let's look at a little bit more details of physics here, okay? So there are cases thin film interference. So let us say, I'm going to make two different things here. So let us see, this is one. Let's say we have a boundary here, okay, some boundary. What does that mean is, this material has a different reflective index. Let's say it has a refractive index or index of refraction N1. This material has a refractive index N2, okay, and this is a boundary. Alright. Now, if we have a light wave incident to this boundary, what happens is this. Right, let's say there is a wave, goes like this. Two things can happen once it gets to this boundary. either it can reflect back, okay. So the case 1 is, let's say, when n1 is greater than n2, meaning this material where the speed of the light is going to be greater, okay. And then this material, that means that is also to say that it's a rare substance, okay. This is called denser, more dense and then more rare, okay. This refractive index has to do with that too. So if we have two cases, so one case is, let's say we have this material that light is traveling from the higher refractive index to the lower refractive index material. Example would be from, like just like this, right? From air to the water. What would happen? Let's see, what would happen? So what would happen is actually, so when there is a light that travels from a high refractive index to the lower refractive index, in the boundary, what could happen is the light would just reflect back without any phase change, meaning it's gonna just reflect back, just gonna look like the way we had before, okay? So no phase change, so no phase change, but it reflects back, okay. So initially it was going this way. Now what happens if we have n1 is smaller than n2, meaning the light is going from a medium with the lower refractive index to the medium with high refractive index. Now instead of light going from air to water, now it's coming from water to air. What happens? Okay, so what do you think would happen over there? So it turns out that the refractive wave would be, instead of going this way, it is actually will have a phase change, so it's going to look like this. Oops. Okay, so it will have, this is reflected back, but then this light, look at this is, it was going, right, it was like this, but then this is coming out, right, like that, okay. So there is a phase change, meaning they kind of cancels out each other, right? Remember, we talked about this when we were talking about the destructive interference, okay. So for this case, phase change occur, and then the path and the phase change actually occur by lambda by 2, so that path phase change would be, or path difference would be by lambda by 2, okay. So these two cases are possible. Okay, so if this phase change occur, meaning light has to go from medium where the refractive index is lower, and it has to go to the higher refractive index region, then the phase changes occur. Okay, so this is the thing we learn here. So then what happens is there could be just not one phase change. If there is like just there could be actually more than one reflective phase change, okay? But then if we have, so there is something called condition for reflective condition for destructive interference with only one reflective phase change. This is given by T equal to m lambda dash by 2. So remember the condition for it says destructive interference with only one reflective phase change. This is also same as the, this also is a condition for constructive interference with 0 or 2 phase change, okay? So this condition is, it could be either for constructive interference or for destructive interference depending upon the number of the reflective phase change, okay? So now you may be wondering, well, what is this T and things you are talking about? So this T turns out to be, T is thickness of film. So in the case of, soap bubble, the T would be the thickness of the soap film, okay? So here this T, and then you guys know now, right? M is just remember M is 0, 1, 2, 3, like before. I mean 1, 2, 3, like integer, and then lambda dash is the wavelength of the wave in a material, wavelength of the light in a material, okay, not in the vacuum. That's the thing. And then for condition for constructive interference with only one reflective phase change is given by this here. Okay, so T equal to m plus half lambda dash by 2. You guys may be wondering, this is kind of looks a little bit what you guys have seen before, but then also you don't know how to relate it, so we will make it relate. So this condition is for condition for constructive interference with only one reflective phase change. So remember, for constructive interference to happen, what did we need? Difference was what? We did like a delta D equal to what? M times lambda, right? If we just had that sound wave, this was for analogy, okay? Sound wave, for this is for delta D equal to m lambda, right, for constructive interference. Now instead of so instead of delta D, we have, that is delta D was the path length difference. For here in the case of thin films, that path length delta D is actually the thickness of the film, okay? So thickness of the film is just T, alright? So that's how we get that, okay? And then you may be wondering, why is there a 2? Because in the boundary, light goes in, but then when light also enters, it also needs to reflect